An accidental electrocution death occurred due to a frayed wire making contact with the manhole lid. This incident resulted in the tragic loss of a 4-year-old child who stepped on the manhole lid and then touched a nearby fence. The manhole lid had become electrified because of the frayed wire. The incident happened in Gallatin, Tennessee, in July of this year. Following this tragic event, investigations were launched by the Gallatin Police Department and the Tennessee Bureau of Investigation to determine the exact cause and circumstances surrounding the electrocution. Electrical safety is paramount in preventing accidents, especially in public spaces where children are present. Frayed or damaged wires pose a significant risk of electrical shock, potentially leading to severe injury or death. Manhole lids and other metallic infrastructure must be properly grounded and insulated to prevent them from becoming energized in the event of a fault. Regular inspections and maintenance of electrical systems are crucial for identifying and addressing potential hazards before they result in accidents. In the event of a suspected electrical hazard, it is essential to maintain a safe distance and immediately notify the appropriate authorities or qualified electricians. Education and awareness campaigns can play a vital role in informing the public about the dangers of electricity and how to avoid electrical accidents. Grounding is a critical safety measure in electrical systems. It provides a path for fault current to flow back to the source, tripping a circuit breaker or fuse and energizing the circuit. This helps to prevent electrical shock and fire hazards. Without proper grounding, metallic objects such as manhole lids, fences, and other equipment can become energized if there is a fault in the electrical system. Insulation is another essential safety measure. It prevents current from flowing through unintended paths. Wires and cables are typically insulated with a non-conductive material such as plastic or rubber. However, insulation can degrade over time due to factors such as heat, moisture, and physical damage. This can lead to exposed conductors and an increased risk of electrical shock. Regular inspections can identify damaged insulation and allow for timely repairs or replacements. Circuit breakers and fuses are overcurrent protection devices that are designed to interrupt the flow of current in a circuit if it exceeds a safe level. This helps to prevent damage to equipment and reduce the risk of electrical shock and fire. Circuit breakers can be reset after they trip, while fuses must be replaced. Ground fault circuit interrupters, or GFCIs, are devices that are designed to detect ground faults. A ground fault occurs when current flows through an unintended path to ground. GFCIs can quickly interrupt the flow of current in the event of a ground fault, preventing electrical shock. GFCIs are commonly used in areas where there is a high risk of exposure to water, such as bathrooms, kitchens, and outdoor locations. Lockout-tagout procedures are used to prevent accidental energization of equipment during maintenance or repair. These procedures involve disconnecting the equipment from its power source and attaching a lock and tag to the disconnect switch to prevent it from being turned on. Only authorized personnel are allowed to remove the lock and tag. Electrical safety training is essential for anyone who works with or around electricity. Training should cover topics such as electrical hazards, safe work practices, and the proper use of personal protective equipment. Qualified electrical workers should be trained in the specific tasks they will be performing. Personal protective equipment, or PPE, is used to protect workers from electrical hazards. PPE can include items such as rubber gloves, insulated tools, and arc flash suits. The type of PPE required will depend on the specific hazards present. Safe work practices are essential for preventing electrical accidents. These practices can include things like de-energizing equipment before working on it, using insulated tools, and maintaining a safe distance from energized parts. Regularly inspect electrical equipment for damage such as frayed wires or loose connections. Repair or replace damaged equipment immediately. Ensure that all electrical outlets and switches are properly grounded. Do not overload electrical outlets or circuits. Use extension cords safely and only for temporary use. Keep electrical cords away from water and heat. Never touch electrical equipment with wet hands. Be aware of the location of overhead power lines and maintain a safe distance. Call a qualified electrician for any electrical repairs or installations. If you see a downed power line, stay away from it and call the power company immediately. If someone is being shocked, do not touch them directly. Use a non-conductive object such as a wooden broom handle to separate them from the source of electricity. Call emergency services immediately. Remember that electricity can be dangerous, and it is important to take precautions to prevent accidents. In any electrical accident situation, calling emergency services such as 911 is the top priority. They can dispatch trained medical personnel and first responders to provide immediate assistance to the victim. While waiting for emergency services to arrive, it is important to ensure the safety of the scene and prevent further injuries. Keep bystanders away from the area and warn them of the potential dangers. If it is safe to do so, turn off the power to the affected circuit or appliance. This can help to reduce the risk of further electrical shock. However, do not attempt to turn off the power if you are standing in water or if you are unsure of how to do so safely. Once the power is off, you can attempt to provide first aid to the victim. Check for signs of breathing and circulation. If the victim is not breathing, begin CPR. If the victim is breathing, place them in the recovery position. Cover the victim with a blanket to keep them warm. Stay with the victim until emergency services arrive. When emergency services arrive, provide them with as much information as possible about the incident. Tell them what happened, what type of electricity was involved, and what first aid has been provided. The National Electrical Code, or NEC, provides comprehensive standards for electrical installations. It is important to follow the NEC when designing, installing, and maintaining electrical systems. The NEC is updated every 3 years to reflect changes in technology and best practices. Article 90.1 of the NEC outlines the purpose of the code, stating that it is intended to provide practical safeguarding of persons and property from hazards arising from the use of electricity. Chapter 1 of the NEC covers general requirements, including definitions, wiring methods, and grounding and bonding. Chapter 2 covers wiring and protection, including overcurrent protection, grounding, and wiring methods. Chapter 3 covers wiring methods and materials, including cables, conduits, and raceways. Chapter 4 covers equipment for general use, including appliances, lighting, and motors. Chapter 5 covers special occupancies, including hazardous locations, healthcare facilities, and places of assembly. Chapter 6 covers special equipment, including elevators, electric signs, and electric vehicles. Chapter 7 covers special conditions, including emergency systems, fire alarm systems, and communications systems. Chapter 8 covers communications systems, including telephone, data, and CAT-EV systems. Chapter 9 contains tables and examples for use with the NEC. Table 310.15b16 provides ampacity ratings for conductors based on insulation type and ambient temperature. Table 250.122 provides minimum equipment grounding conductor sizes. Table 430.250 provides full load current ratings for 3-phase alternating current motors. Article 250 of the NEC covers grounding and bonding requirements. Grounding is the intentional connection of a circuit or equipment to the earth. Bonding is the connection of metallic parts to form an electrically conductive path. Grounding and bonding are essential for safety, as they provide a path for fault current to flow back to the source, tripping a circuit breaker or fuse and de-energizing the circuit. This helps to prevent electrical shock and fire hazards. Section 250.4 FIV requires that grounding electrode systems be bonded together to create a low-impedance ground path. Section 250.24c requires that the neutral conductor be grounded at the service entrance. Section 250.118 less acceptable grounding electrode conductors. Article 300 of the NEC covers wiring methods. Wiring methods refer to the way in which electrical conductors are installed and protected. The NEC specifies different wiring methods for different applications, depending on factors such as voltage, current, and location. Section 300.3b requires that all conductors of a circuit be installed in the same raceway, cable, or enclosure. Section 300.4d requires that cables and raceways be protected from physical damage. Section 300.11 requires that wiring be securely supported. Article 400 of the NEC covers flexible cords and cables. Flexible cords and cables are used to connect portable appliances and equipment to a power source. The NEC specifies different types of flexible cords and cables for different applications. Section 400.7 lists permitted uses for flexible cords and cables. Section 400.8 lists prohibited uses for flexible cords and cables. Section 400.24 specifies ampacity ratings for flexible cords and cables. Article 430 of the NEC covers motors, motor circuits, and controllers. Motors are used to power a wide variety of equipment, from small appliances to large industrial machinery. The NEC specifies requirements for motor protection, control, and wiring. Section 430.22 specifies the ampacity of conductors supplying motors. Section 430.52 specifies overcurrent protection requirements for motors. Section 430.83 specifies controller requirements for motors. Article 440 of the NEC covers air conditioning and refrigeration equipment. Air conditioning and refrigeration equipment use motors to drive compressors and fans. The NEC specifies requirements for the installation, protection, and control of air conditioning and refrigeration equipment. Section 440.62 specifies the ampacity of conductors supplying air conditioning and refrigeration equipment. Section 440.22 specifies overcurrent protection requirements for air conditioning and refrigeration equipment. Section 440.6 specifies disconnecting means for air conditioning and refrigeration equipment. Article 500 of the NEC covers hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dusts are present. The NEC specifies requirements for electrical equipment installed in hazardous locations to prevent explosions and fires. Section 500.5 defines different classes and divisions of hazardous locations. Section 500.8 specifies requirements for equipment approved for use in hazardous locations. Section 500.7 specifies wiring methods for hazardous locations. Article 517 of the NEC covers healthcare facilities. Healthcare facilities have unique electrical requirements to ensure patient safety. The NEC specifies requirements for essential electrical systems, grounding, and isolated power systems in healthcare facilities. Section 517.30 specifies requirements for essential electrical systems in healthcare facilities. Section 517.13 specifies grounding requirements for healthcare facilities. Section 517.160 specifies requirements for isolated power systems in healthcare facilities. Electrical safety is a shared responsibility. By following safe work practices and adhering to electrical codes, we can all help to prevent electrical accidents and ensure a safe working environment. Understanding the specific electrical hazards associated with a task and taking appropriate precautions are essential. This includes identifying potential sources of electrical shock, arc flash, and arc blast, and using the correct personal protective equipment (PPE). Always de-energize electrical equipment before working on it whenever possible. Use lockout/tagout procedures to ensure that the equipment cannot be accidentally energized while you are working on it. Inspect electrical equipment regularly for damage, such as frayed wires or cracked insulation. Repair or replace damaged equipment immediately. Use insulated tools and equipment when working with electricity. Maintain a safe distance from energized electrical equipment. Never work on electrical equipment while you are wet or standing in water. Be aware of the location of overhead power lines and maintain a safe distance. Call a qualified electrician for any electrical repairs or installations that you are not qualified to perform. Report any electrical hazards that you observe to your supervisor or safety department. Attend electrical safety training courses to stay up to date on the latest safety procedures. Follow all applicable electrical codes and standards. The Occupational Safety and Health Administration, or OSHA, also publishes regulations and guidelines for electrical safety in the workplace. These regulations cover topics such as lockout/tagout, personal protective equipment, and safe work practices. It is important for employers to comply with OSHA regulations to protect their employees from electrical hazards. OSHA Standard 29 Code of Federal Regulations 1910.303 covers general requirements for electrical safety. OSHA Standard 29 Code of Federal Regulations 1910.304 covers wiring design and protection. OSHA Standard 29 Code of Federal Regulations 1910.305 covers wiring methods, components, and equipment for general use. OSHA Standard 29 Code of Federal Regulations 1910.331 covers safety-related work practices. Frayed wires expose the conductive core, creating a direct path for electricity to flow where it shouldn't. This can electrify anything the wire touches, including metal objects like manhole covers and fences, creating a potentially lethal hazard. Even seemingly minor contact with an energized object can cause a shock, leading to muscle contractions, burns, or even cardiac arrest. The severity of the shock depends on factors like the voltage, the amount of current flowing through the body, and the individual's health. Children are particularly vulnerable to electrical shock due to their smaller size and lower resistance. Therefore, it's crucial to maintain vigilance and address any potential electrical hazards promptly, especially in areas frequented by children. The investigation into the Gallatin incident will likely focus on several key areas. Firstly, determining the source of the frayed wire and how it came into contact with the manhole cover. Secondly, assessing whether the electrical system was properly grounded and maintained. Thirdly, evaluating whether there were any violations of electrical codes or safety regulations. Fourthly, identifying any contributing factors that led to the accident. The findings of the investigation will be used to determine whether any parties were negligent and to prevent similar incidents from occurring in the future. This may involve recommending changes to electrical safety practices, increasing inspections of electrical systems, and educating the public about the dangers of electricity. The incident serves as a stark reminder of the importance of electrical safety and the need to take precautions to prevent electrical accidents. By being aware of the hazards and following safe practices, we can help to protect ourselves and others from the dangers of electricity. If you observe a frayed wire or any other potential electrical hazard, report it immediately to the appropriate authorities or a qualified electrician. Do not attempt to repair the hazard yourself unless you are a qualified electrician. Stay away from downed power lines and treat them as if they are energized. If you see someone who has been shocked by electricity, do not touch them. Call emergency services immediately.